Okay, 2.6, rational functions and their graphs. All right, so first of all, what would a rational function look like? Does anybody remember? You know, I know it's been spring break, but think about it for a second here. What is a rational function going to look like? Like this? Like a fraction? Oh, you're talking about the graph of it? Okay. So the function itself looks like a what? What does rational mean to you? A rational number means it can be written as a fraction. The word rational and the word fraction ought to be joined together in your mind in a math class. Okay? Rational does not mean someone who is sane and reasonable. Okay? It means something that can be written as a fraction. So a rational function is going to look something of the form where you've got one polynomial. So r of x, let's call it a rational function, is some p of x divided by q of x, where p and q are polynomials. Okay? So in other words, those exponents are going to be positive whole numbers. Okay? That's what a rational function looks like. Now, if I have a polynomial in the denominator, so there's some x's down there, what am I going to have to be careful of? What can I not have in the bottom of a fraction? No, not a square. I can have square roots in the bottom of a fraction all day long. Can't be equal to 0. So I'm going to have places in my graph where I am undefined, most likely, right? Anytime you've got a letter in the denominator of a fraction, you've got to figure out whether or not you can get a 0 down there. And if you can, that cannot be in the domain. So the first objective here is talking about the domain of rational functions. So the domain of a rational function must be restricted so that any number that gives a value of 0 for the denominator is not allowed in the domain. Okay, that took me too long to write it, so I'm afraid I didn't say what I needed to say. The domain of a rational function must be restricted so that any number that gives a value of 0 for the denominator is not allowed in the domain, okay, or can't be used. So example 1, checkpoint 1. So f of x is equal to x squared minus 25 over x minus 5. B g of x is equal to x over x squared minus 25, and C h of x plus 5 over x squared plus 25. Okay, so we're supposed to be finding the domain of each one of these functions. Now, the domain, remember, starts out being what? What does the domain of any function start out being? All real numbers, except for, and then we find the exclusions, right? Okay. So, what part is not allowed? What can I not have? 0 in the bottom. So I'm going to take the denominator and I'm going to set it equal to 0 to find out where my trouble spots are. So how do I solve this? Add 5 to both sides. So x is equal to 5. That's my trouble spot. So my domain, we used to write as, we just say x is not equal to 5. Okay, now in this book, and in a lot of different places where you take tests, what they do is they write it in interval notation. We've been talking about interval notation, right? So if you were going to write this in interval notation, this is from a negative infinity up to 5. It doesn't include 5, so put the parentheses, right? And unioned with from 5 to a positive infinity. So that's interval notation, which says to you that you can use every number in the world except for 5. That's how you read that. So if you see an interval notation written this way, that's what that means. I can use everything except 5 because I don't have the square brackets around the 5. It means 5's not included. It means I can use 4.99999 and I can use 5.000001, but I can't use 5. Okay? So if you see that in the book, that means the same thing as what we've always used before. It's just a different way of writing it. Okay? We good? All right. Now, what do I do with part B? How do I find out the domain? Just set the bottom equal to 0. That's how you do it every single time. Now, how am I going to solve this? Add 25 to both sides. Or you could have factored it, right? Now, when you take the square root of this, what do you have to be real careful about? Get both of your answers, which means you take a positive and a negative 5, right? Square root of 25 is 5, and when you take the square root solving something, then it was a positive 5 and a negative 5. Okay. So my domain is everything except that. Okay, so the shortest way to write that is that way. Again, what you may see on some standardized tests or some multiple choice tests is that's from a negative infinity up to negative 5, from negative 5 up to positive 5, and then from 5 to a positive infinity. Okay? Do you need me to fix that where you can see that better? I don't remember. I just know I've seen it both ways. So I just need you to know that they mean the same thing. Okay, so on part C, what are we going to do? Same thing. What does same thing mean? Set the bottom equal to 0 to find the domain. Okay, now what am I going to do? Subtract 25 from both sides. So I get x squared is equal to a negative 25. Is that going to be a real number? No. So that means to me that I don't have to restrict anything. There's never going to be a time when I put a number in for x that I'm going to get a 0 in the denominator because this is not a real number and I'm only going to put real numbers in, right? So that means my domain here is what? All real numbers. Because we don't have to worry about restricting complex numbers out or imaginary numbers out. Right? And if you want to write that in interval notation, and it is, you know, that just means from negative infinity to positive infinity. Any questions about the domain? It's that easy. Anytime you have a fraction where there's a letter in the denominator of the fraction, you got to make sure that you don't have numbers that cause zeros in the denominator. Okay. Objective 2 says they want you to be able to use the arrow notation. So when we have this idea of a rational function, a lot of times what happens with the graph is at these places where I've got these zeros on the bottom that cause me undefined, I get these things called asymptotes. And the graph does not look the same on the left and on the right always on each side of the asymptote. So we need to talk about what's happening on the left side of the asymptote and what's happening on the right side. And this is an idea we use a lot in calculus next year. Okay, so if I use this arrow notation and I write this, what that means is as x approaches 1. So I'm talking about what's happening at point 99999 and what's happening at point 99999, right, as I'm getting closer and closer to 1. And it also talks about what's happening when I'm at 1.00001 or 1.001 or 1.01, right? So I can approach from the left or from the right. So we have to have a way to notate that because sometimes we're talking about different sides. So if you have an arrow that looks like this, where there's a little negative sign hanging up there in the air as a superscript, that means as we approach x, as x approaches 1 from the left. So you're going to look on the left-hand side of 1 to see what's going on. And then if it says as x approaches 1 and it's got a little plus sign up there, then it's talking about from the, anybody got a guess? Right side. That means as x approaches 1, whoops, from the right. Okay? That's just a notation. You just need to be able to read it. Okay. Not only do we approach certain numbers, that we also talk about what's happening as x approaches infinity and as x approaches, whoops, yeah, -8, negative infinity. Okay, so this means what's going on with my graph as I get way to the, where's positive infinity? Right-hand side of the graph. And this says what's going on way over there on the left-hand side. Okay? Everybody understand? We use this notation a lot with calculus because we talk about limits. One of the main ideas of calculus is that as I get closer and closer to this value that's maybe undefined, I can get an answer that tells me what I need or that I can work with. And so we talk about the limit. We talk about what's happening as I get really, really close to this place. Maybe from the left, maybe from the right, maybe from both sides. So you're going to see this notation. You really need to know what this means. Okay? And we'll talk a little bit more about limits after we take the test for Precal, when we do the intro stuff. Y'all will be glad we did. The kids this year said that it really helped. They actually really did remember it. All right. Now, we need that notation in this particular section because we're going to talk about vertical asymptotes. sorry. Vertical asymptotes can only happen when the denominators are equal to 0. Now, I'm not saying that every place where the denominator is equal to 0 we get a vertical asymptote. What I am saying, though, is that you cannot have a vertical asymptote unless there's a 0 there in the denominator. Does everybody understand what I just said? Because sometimes we get something called a removable discontinuity. In other words, it's just a hole in the graph. So everywhere that you have a 0 in the denominator, in other words, where you don't have your where the domain's not defined, that's either a hole in the graph or an asymptote. Okay? Now I'll show you the difference in just a second. We have to find those, so what do you think we need to do to find the vertical asymptotes? Vertical asymptotes only happen places where you don't have the domain defined. How would I find a vertical asymptote? Set the bottom equal to 0. The exact same process you used for the domain. I want you to understand this. The part that I took out of the domain, that's the part that is the vertical asymptote. Okay? So when you find one, you found them both. Okay? Don't do double work. I've had kids in the past that go, I know I need to do something to do this. They've already done the work. Okay? Sometimes you can do the work once and get a couple of different pieces of information from it. We like that, don't we? All right, checkpoint 2 then. Let's find some. Or example 2, whatever you want to call it. So f of x is equal to x over x squared minus 1. B, g of x is equal to x minus 1 over x squared minus 1. And C, x minus 1 over x squared plus 1. All right. So let's find our vertical asymptote. So I'm going to take the denominator, set it equal to 0. Right? Now, y'all want to factor this or y'all want to just add a 1 to both sides? Which way do y'all like this? I'm factoring it. We did the other way. So this is x plus 1, x minus 1, right? Difference of 2 squares. Remember the quick factors nicely, and then I've got x plus 1 is equal to 0 and x minus 1 is equal to 0. So x is equal to negative 1 and x is equal to a positive 1. This is the equation of both of your asymptotes. The equation for a vertical line is x equals a number, right? Everybody understand? So when you set it equal to 0 and you solve it, you have found the equation for the vertical asymptote, and that's what they're asking for. So this is a vertical asymptote, and this is the equation for a vertical asymptote. They are both asymptotes because I can't factor anything out the top, right? So if I rewrite that as x over x plus 1 and x minus 1, nothing factors out here. Everybody understand what I just said? Nothing factors out. If nothing factors out, then they stay vertical asymptotes. Look at B. I take the denominator and factor it. What am I going to get? X plus 1 and x minus 1, right? Didn't we just get through saying that? The difference with B as opposed to A is that if you look at this, there's an x minus 1 on the top and the bottom. So if we were doing this back in Algebra 2, what would we do? We'd cancel those out, right? They'd reduce down to 1s. what this tells us with vertical asymptotes, is that x plus 1 equal to 0, which gives me x equals -1. That's an asymptote. That's the equation for a vertical asymptote. This one that canceled out, it's still there. It's still a problem. I still can't use +1. But this one is not an asymptote. This one's a hole in the graph. So in other words, the graph will come up to it. It's got this little hole that will skip over, and it'll keep going at the same place. Okay? This one's called a removable discontinuity. I don't know if y'all remember that from last year. We talked about these in Algebra 2. Okay? So it's a hole, or a removable discontinuity. I think in this book they don't really call them removable discontinuities. They just call it a discontinuity. Okay, so do y'all see the difference? Here I have two vertical asymptotes. Here I've got one vertical asymptote and one that's just a hole, a gap, a place I skip over. It's like you're drawing along, pick up your pencil, put it on the other side, and then keep drawing. Okay? That doesn't happen with vertical asymptotes. On the vertical asymptotes, what happens is your graph either shoots off to a negative infinity or up to a positive infinity along it. Okay? All right, and then on part C, I have x squared plus 1 equals 0. So am I going to be, is there anything that I can put in there where I'm going to get a 0? X squared is always going to be positive, right? If I add it to any number, am I ever going to get a 0? No, to get 0, you got to have one of them negative, one of them positive, right? So this is not going to take anything out, so I just will not have, I'll have no vertical asymptotes here, because my domain is all real numbers. Okay? So those are the three things that can happen to you when you're finding vertical asymptotes. Everything in the denominator gives you a vertical asymptote. Some things give you vertical asymptotes, some things give you a discontinuity, and then you get no vertical asymptotes at all. Questions? All right. So, objective 4 then. Talked about vertical asymptotes. We're going to be talking about horizontal asymptotes now. Horizontal asymptotes are totally tied to the degrees of the numerators and the denominators. It's a comparison. Remember that we talked about this before. This is called end behavior. That's what horizontal asymptotes tell you, end behavior. Doesn't even apply to the middle. It's talking about what's going on with this graph as x approaches a positive infinity and what's happening as x approaches a negative infinity. Because what happens with these graphs is they a lot of times will kind of come to this point where they're getting very, very close and they won't cross over that line anymore. And I don't know if you remember how we did this, but remember I told you that r of x a lot of times is notated as p of x divided by q of x. Right, where p of x is a polynomial and q of x is a polynomial. Now, every polynomial has a degree. Does anybody remember what the degree of the polynomial is? The highest exponent on any one term, right? Okay? So, when we talk about this, if we let m equal the degree of p of x, and n equal the degree of q of x. It makes my life so much easier. Okay? Caden? What you're going to be doing is you're going to be comparing the degrees of the top and the bottom. So you have three cases. If the top degree is greater than the bottom degree, the degree of the top is larger than the degree of the bottom, then there is no horizontal asymptote. You actually get something called a slant asymptote. We'll work with that more. If the degree of the top is less than the degree of the bottom, if that's the case, then the horizontal asymptote is y is equal to 0. It's just that simple. So in other words, out at the ends, I can just get close to the x-axis. That's where I go. There is one last case. Anybody know what it is? If they're equal to each other, right? This one's bigger, and the other one's bigger. The last one is that they're equal to each other. Yes? Then there is a horizontal asymptote, and the horizontal asymptote is y is equal to the leading coefficient of the top over the leading coefficient of the bottom. Okay, so you don't move them around, so I'm just going to write leading coefficient over leading coefficient. Now, somebody tell me what the leading coefficient is. What does that word mean? It's the number in front of the term with the highest degree, right? Okay, so there are your rules. It is on the bottom of page 345 if you want to, like, have a place to look back at that. So let's look at checkpoint 3. All right, let's find the horizontal asymptotes. So, the degree of the top on A is what? 2. The degree of the bottom is 2. So, M is equal to N here, right? So, remember we said the horizontal asymptote is y is equal to the leading coefficient of the top, which is what? 9, over the leading coefficient of the bottom, which is 3. Everybody understand that? So my horizontal asymptote here is y is equal to 3. So that means on the left and the right-hand side, out at the ends, not in the middle, it'll either come up to 3 or down to 3, but it won't go past it at the ends. Okay? Kind of like these wings that are out there, kind of holding it. It's a part of the framework. Any questions about that? Let's look at B. What do we know about the degree of the top as compared to the degree of the bottom? M is less than N, so what is it? Y equals 0. No work on that one. No really work on any of them. Okay? Part C, what do I know about the degrees and how they're related? M is greater than N, so what did that mean to us? Not 1. No horizontal asymptote. Okay? So any questions about that? We're good? Next objective then. Objective 5. We're going to talk about how to use transformations. To graph rational functions. Okay, so there are some of these rational functions that they give me that are kind of in a different form than what I've been talking about. I have only shown you examples of where it's one polynomial divided by another polynomial. They don't always give it to you that way. The rational function, parent function. Does anybody remember what that is? Y is equal to 1 over x. That's it. That's the rational parent function right there. Remember what it looked like, its graph from last year? Because what's true about this? Does it have a vertical asymptote? What's its vertical asymptote? X equals 0. Right? It's not 0, it's x equals 0. When it asks for an asymptote, it wants the equation of the line. This is the line, x equals 0. Everybody understand? Okay? Now, what's the horizontal asymptote of this thing? Y equals 0. Do I still hear people saying 0? Why is it y equals 0? How does that go with what we talked about a minute ago? What's the degree of the top? If it doesn't have an x, its degree is 0, if you don't remember that. The degree of the top is 0, the degree of the bottom is 1, so the top is less than the bottom, right? And every time the degree of the top is less than the degree of the bottom, then my horizontal asymptote is y is equal to 0. Okay? All right, so this is my parent function. You see how it fits in with that other stuff that we've already been talking about. All right, so remember with transformations, we had things of the form where they were moving around. So if I like added or subtracted something to the x part of the equation in parentheses, it moved it left and right, right? If I added it or subtracted it to the whole equation, it moves it up or down. And if I multiply by something, then it dilates it, stretches it out. Or it can reflect it if I multiply by a negative number, right? So let me tell you, your transformation form of this looks like this. F of x is equal to a over x minus h plus k, where a is that dilation factor. And if it's negative, it's flipped upside down, right? If it's positive, then it's in the same orientation as the parent function. If it's got a number subtracted from x, then I've actually moved it to the right. So what's actually going to move? What's my point that I'm probably going to move around to be able to see what's going on with this thing? My vertical asymptote, right? If I slide it over, then I can draw the rest of it kind of in relationship to it. Okay, my vertical asymptotes and my horizontal asymptotes are my guidelines, my skeleton that I hang my graph on. Okay, so if it says x minus a number, we've moved it to the right. If it says x plus a number in the denominator, I've moved it to the left. And what I'm going to move is I'm going to move my asymptote and then hang the rest of it on it. Everybody understand what I'm talking about? Now, if I've got a number added to the entire function sitting at the end, not part of the fraction, then I've moved the graph up. What am I going to actually move up? The whole thing. But what's going to help me hang the graph? What's my skeleton that helps me hang the graph? The horizontal asymptote. The K affects the horizontal asymptote. And if I've subtracted a number, I'm going to take the horizontal asymptote and move it down. Okay? So, keep in mind what the original one looks like. And also they're going to give you some others here. Checkpoint 4. Okay, so it says use the graph of f of x equal to 1 over x. That's the one we just did, right? That's our parent function that we're going to be working with. And we are going to graph g of x is equal to 1 over x plus 2 minus 1. So do I have any dilation? No. Do I have any flip, reflection? No, because it's a positive 1. But I do have a move to the, so the vertical asymptote I'm going to move to the left, to left. And the horizontal asymptote I'm going to move 1 down. Okay? So I'm going to go over here to -2 and draw in my vertical asymptote. And I'm going to go down to a -1 and draw in my horizontal asymptote. And remember, that only applies out in the ends, so I don't have to draw it all the way across. And then, remember my original function? This side is down below. I'm going to draw in that piece. And I'm going to draw in that piece. Okay? Now, you can make this a better drawing. How? I mean, I kind of just slid it on there. How can you make it a more accurate drawing so I don't take points off when I'm actually grading? What do you need? Some points on the graph, right? So where could you get your points from? Calculator. That's exactly right. I expect you to take this equation, put that in the calculator, and then look at the table. Now, I'm going to advise you not to look at the graph and try to just draw it off the graph, because that's going to mess you up. What you need to do is locate your horizontal asymptote and your vertical asymptotes, and then get some more points, and then just fill in with that. Because what happens is with your calculator, with these rational functions, it'll draw through, because what it does is it plots a point and it plots a point. And sometimes it drags through there, not because the calculator thinks there's not a hole there. If you look at the table, you'll see your hole. But the way the calculator draws the picture, you can't see the hole on the graph. Does that make sense? So it just drags from one point to the next is what it does. Okay? Any questions? It's really bad when your asymptote, because see how my asymptote here, that they go like this? Well, you can see that on your graph. But if you have this thing going on with your graph, sometimes that drags across there too, and it doesn't always show up. Sometimes it does, but sometimes it does not. So I'm just telling you, the graphs for rational functions, you do not need to just look at the graph and then just try to draw me the picture that's on your screen of your calculator, because you will miss some stuff. Do use it, though, to get some points to plot it to get a more accurate drawing. Okay? Any questions about how to use these transformations to move things around? Yes, no? Y'all got that? Those should be quick and easy for you to do. Last objective, I think, in this section is we're going to talk about actually how to graph these things. No, I lied. Yep. If you will look on the bottom of page 347, that gives you the steps for the graph. Okay? We're just going to go through and graph one. So checkpoint 5. Y'all ready? First thing I always check is I look to see if anything's going to factor out. And I can factor the 3 out of the top here, but that's going to leave me 3 times x minus 1, and nothing's going to reduce, right? So I don't have to worry about any discontinuities as opposed to asymptotes. So I look at that first. I find my vertical asymptotes. How do you find the vertical asymptotes? Bottom equal to 0. So x is equal to 2. And I start building my skeleton that gives me my framework to be able to draw this graph. So I go over to where x is equal to 2, and I draw in my vertical asymptote. Now I get my horizontal asymptote. Okay, how do you get the horizontal asymptote? Check the degree of the top and the degree of the bottom. So the degree of the top is 1, the degree of the bottom is 1, so they're the same. So my horizontal asymptote is y is equal to, what's the leading coefficient of the top? 3. What's the leading coefficient of the bottom? So y equals 3. So out here on the ends, remember not necessarily in the middle, my graph's going to come up and touch that. Okay? Now I am going to go ahead and find the intercepts by hand, because I don't like looking for those on the calculator. You know, in the table. I don't mind you going to the table and finding yourself some points, but sometimes those aren't exact numbers, and it's just much easier to find them. So if I find the x-intercepts, how do I find x-intercepts? What's true about every x-intercept? Y is equal to 0, right? So I get that 0 is equal to 3x minus 3 over x minus 2. Now, can x minus 2 be 0? If I have a fraction and my fraction is 0, the only way that happens is what? If the top is equal to 0. So I don't have to do the whole thing. All I need to do is find out where is the top equal to 0. That gives me my x-intercepts. Okay? So you set the bottom equal to 0 to find your vertical asymptote. You set the top equal to 0 to find your x-intercepts. So I add 3 to both sides, and I divide by 3. So x equals 1. So I'm going to cross the x-axis at 1. Found a point. Okay? Now I also always find my y-intercept. How do you find the y-intercept? X's are zeros, so y is equal to 3 times 0 minus 3 over 0 minus 2. Right? So y is equal to 0 minus 3 is negative 3, and 0 minus 2 is negative 2. So at positive 1.5, so I'm going to cross the y-axis right here. Okay, we good? Now let me tell you, you've just found the only places where I can cross the y-axis or the x-axis. So when I start looking at this and I draw this, well, I know that I can only come up here to get close to this, and I can only get close to that. I can't cross those two. Those are my framework that I draw off of, right? I could start down here and come up to here, but what's true? Am I going to cross the x-axis anywhere else? No, I found all the places where I can cross the x-axis. So I can't start down here and go up to the horizontal asymptote. So where must I be for the other half of this graph? Up here in the top, right? I got to start up at the top and come down to it. The way you double check that and make sure that you figured out where to draw it is you go to the table on your calculator and you give yourself some points. And so what I want to see on your paper is that you've gone in and given yourself some more points so you can locate exactly where your graph draws. So you're probably going to need between 3 to 5, maybe even 7 more points to be able to draw a good graph. Everybody understand what I just said? Y'all are all asleep. It's not spring break anymore. Okay? Those are my 5 steps. Now, they give you many more steps than that. You can do whatever you want with that. But these are my 5 steps, and these are the only steps I expect you to show me. Where you have found the vertical asymptotes, where you found the horizontal asymptotes, where you found the x-intercepts, where you found the y-intercepts, and then some more points that you got off the table. Okay? That's what I need to see on your paper when you draw me a graph, because I will be looking for those things separately from the graph. Don't just draw me a graph and expect to get the credit for it. I want to see these things labeled so I know you know what you're looking for. It should say vertical asymptote, x equals a number. Horizontal asymptote, y equals a number. X-intercept, x equals a number. Y-intercept, y equals a number. Everybody understand? All right. Okay. They give you several more examples of that, just different different things that come up, different ways it can look. I want to skip on over to Objective 7 because you use the same exact 5 steps every single time, y'all. Okay? Because if you'll remember a while ago, we talked about something, and I said, doesn't have a horizontal asymptote, it has something called a slant asymptote, right? This is about how to find the slant asymptote. So, checkpoint 8. F of x is equal to 2x squared minus 5x plus 7 over x minus 2. Okay, I'm not going to worry with factoring the top. Now, probably don't need to anyway. Might as well go ahead. Let's see if we can factor the top. Remember, step number 1 is always see if the top and the bottom will factor, and it's got an x squared in the top. So I'm going to do a bottoms up. So I've got x squared minus 5x plus 14. Remember how to do bottoms up? And then the two things that, what? That's what I'm doing right now, reminding you. You take the number in front of the x squared and multiply it by the last number. Now you factor this, if you can. What are the things that multiply together to give you a positive 14? Positive 7, positive 2, or negative 7 and negative 2, right? Is there any way that if I have a positive 7 and positive 2, or can't get a negative 5 out of it, right? Everybody understand? I could get it out of there if it was a negative 14. But both either got to be positive or both got to be negative, so I'm either going to get a positive 9 or a negative 9 when I add them together. Okay, so this one doesn't factor, so I don't have to worry about it. Okay, so vertical asymptote. That's my vertical asymptote. How do I find it? Y'all wake up. It's x equals 2. I don't have a horizontal asymptote. I have a slant asymptote. Okay? This is how you find the slant asymptote. Does everybody know how I knew? The degree of the top was greater than the degree of the bottom. Anytime the degree of the top is greater than the degree of the bottom, there is no horizontal asymptote. If you have one, it's a slant asymptote. Okay? Now, this one is a slant asymptote because not only is the degree of the top greater than the degree of the bottom, but it's greater by just 1. If it's greater by just 1, then this gives you a slant asymptote. See, 2 is 1 bigger than 1. Okay? I'm just making sure we're good here. Okay? That's part of the requirements. This is how you find the slant asymptote. You take the bottom and divide it into the top. Into the top of the rational function. So we're going to do a long division or a synthetic division. This one actually works with synthetic division. We could do it that way. So 2x squared divided by x gives me 2x, right? Yes? So I got 2x times x gives me 2x squared. 2x times negative 2 gives me negative 4x. Change the signs, right? 0 pair like it's supposed to be, negative x plus 7. Everybody following me? We're good? You remember how to do long division? And now x divided into negative x gives me what? Negative 1. So negative 1 needs to go on the top. So I got negative x plus 3. Change the signs, 0 pair, that gives me 10. I don't care about the remainder on this. The equation for the slant asymptote is whatever you get up here. So the equation for the slant asymptote here is y is equal to 2x minus 1. Okay? That's my other piece of my framework. So I have a vertical asymptote at 2. My slant asymptote follows along this line, 2x minus 1. So at negative 1 I have a point, and my slope says go up 2 and over 1, right? So if I were to draw that, then I get this right here. Everybody see what I just did? Now, my graph is going to live between these two limits. Or it could do this and this. I don't know. How do I figure out where the graph itself lives? Because this is just my framework, right? My asymptotes just give me my framework to hang my graph on. I have to actually find points to locate the thing. What are some points that I could use? X and Y intercepts. The y-intercept's the easy one, right? I can get rid of all the x's because zeros go in for it. And so I get 7 over negative 2. Right? Okay, which is what, 3.5? Negative 3.5? So it's right there. That means this piece down here has got to look something like this. Because it's got to live somewhere around those, right? Everybody understand that? Now I need to know whether this other piece lives here or if it lives up here. Probably not going to cross the x-axis, right? How would I find out? Calculator, okay? Or you could take the numerator and set it equal to 0, right? But we just said a minute ago it wouldn't factor, right? So we'd have to put that into the quadratic formula. So I'm with Anthony. It'd be much quicker and easier to take this equation and put it in y equals and then look in my table and see what's going on with these points. And do I have any points over here or are they actually up here? And just find you some more points. So again, your last step on this is always going to be to get that table and get me some more x and y values. So since this is 2, I'd like for you to tell me in your table what y goes with 3. Because that's the piece I need to know, right? What's happening after x equals 2. So give me a 3, a 4, a 5, I don't care. Give me some points. 3 is 10. So I'm thinking I am definitely up in this little area right here. What do y'all think? Okay? Any questions on a slant asymptote? It's just an extra step that you don't have if you have a horizontal asymptote, because you actually have to do that long division to find the equation of the line. Okay? And then we have one last objective. This time I'm really right. Okay. The biggest application that I need to make sure that you're aware of is a business application with rational functions, and it's called the average cost. The average cost, it gives me the selling price for my product if I'm in business and I'm building things. Okay? Most of the time in business, you have some things that are fixed costs, a startup cost, whatever. And so you can't just say, well, it cost me $12 to make this product, so I'm going to sell it for $15. Because you might have had a $10,000 startup cost that you've got to spread out over the cost of every one of your products, because you've got to cover it. I mean, otherwise, then that's just always out of your pocket, and you never make that money back. So the average cost is found by taking the cost function and dividing it by x, where x stands for the number of items. Okay, so if they ask for the average cost, then you're going to take their cost function they give you and divide it by x, where x stands for the number of costs. So it may be an n. I say x, it may be n. Okay? So a cost function, like I said, usually has something in the fixed cost plus the cost per item. So like if we were getting some T-shirts done, then there's a fixed cost. It costs like $500 to set up the screen, just do the screen printing, the silk screen. You know what I'm talking about? $500 for the cost from set up the computer or whatever. Plus, they're going to charge us $5 per T-shirt, where X stands for the number of T-shirts. Okay? That's the cost. In other words, if I order 25 T-shirts, I'm going to take 500 and add it to 5 plus times 25. Everybody understand that idea? So the more T-shirts you order, the less the $500 costs for each one, right? I mean, if you order just one T-shirt, then that T-shirt costs $505. I mean, y'all get that? So a lot of times what we need in business is we need the average cost. So we can figure out how much to charge for each one of these T-shirts so that I can actually make a profit. So the average cost is by taking the cost function, whatever it is, and dividing by X, which is the number of items. That's how much each shirt is going to cost us. Okay? So as you can see, average cost is always a, what type of function? Rational, because it's always going to be over X. Yes? Okay? So that's why they put this as an application here, because average cost is a very valid thing that we use in the business world, and it is always rational. Okay? So just wanted to make sure you were aware of the definition for average cost. The other thing that they use a lot of times is uniform motion. You know the one where the two trains leave the station? How far apart are they after so many miles or whatever? Well, the reason that that's here is because what are you going to use? Distance is equal to rate times time. Yes? So what happens sometimes? When are they going to meet? When are they the same distance apart? What am I looking for when I say when? Time. If I take this and I solve it for time, then that's distance divided by rate. Yes? Now what kind of function do I have? It's rational. Okay, so just remember that on some of these application problems you're going to be using the distance formula, but you won't be using it solved for distance. It'll be solved for time or maybe the rate, because both of those give you a rational function. Anybody got any questions? No? So your homework assignment for this week, let me go ahead and just give you the whole week. Is that what y'all want the whole week, or y'all just want today? All right, so 2.6, we're going to be on page 354, and you're going to do 4 through 100 multiples of 4. So just 25 problems. I know. 2.7 is going to be on page 366, 4 through 80, multiples of 4. And then 2.8, modeling using variation, it's going to be on page 376, 2 through 38, and it is even. So multiples of 2, not 4, that one. Okay, that's the rest of this chapter. So, now we may have to wind up spending more than one day on some of these, but you've got the rest of the chapter homework. Okay. Any questions? Not yet.